Welcome all of you to another EOL seminar. I'm really pleased to present Scott Tyler today as our speaker. Scott is Foundation Professor at the University of Nevada, Reno, with joint appointments in the Department of Geological Sciences and Engineering and the Department of Civil and Environmental Engineering. He's director of the Center for Transformative Environmental Sensing Programs, known as CTEMPS to its friends. And that's an NSF-supported community facility focusing on fiber optic-based sensors and small UASs for Earth surface sensing. Scott holds bachelor's and master's degrees in mechanical engineering. He has a PhD in hydrogeology. He's a fellow of the American Geophysical Union, the Geological Society of America, and the Soil Science Society of America, and he's incoming president of AGU's hydrology section. His research interests are wide-ranging, and they include meltwater dynamics of Antarctic ice shelves, assessing recharge in arid groundwater systems, the role of groundwater surface water interactions in aquatic ecology, quantitative assessment of root dynamics using microcomputed X-ray tomography, the design and operation of salinity gradient solar ponds coupled with membrane distillation for the development of low-cost desalinization, and the impacts of forest management practices on snow hydrology in Mediterranean climates. And he's going to tell us about some of that research today. Scott.
Okay, thank you. Thank you, Mike, and thank you all for inviting me here to visit with you today. I appreciate it. I know it's a really nice day, and I think we'd all rather be outside in the sun. So, but thanks for coming. So this is going to be kind of a wide-ranging talk. I thought I'd throw, since this is the Earth Observing Laboratory, I would throw a lot of different things at you, of different techniques that we've been developing for studying Earth surface processes, if you will. So it's going to be a little discombobulated, and I apologize for that ahead of time, but we're all friends here, so hopefully you'll get something out of it. We're going to focus on most of the talk on Antarctic ice shelf stability, because that's where we've been doing quite a bit of work and new work. It's relatively important for sea level rise. But we'll talk about some drones, some snowmelt, and probably a few other things that we can do with some of the sensors we've been working on. So I don't have to tell this group, I don't think, that the climate is warming. This is just temperature anomalies plotted back over the last roughly 150 years, and indeed things are warming. And obviously this is a great concern to a lot of us for almost everything. But one of the things we often don't think about is issues of sea level rise and the impact on the developed world. We often think sea level rise is going to impact significantly the developing world, the developing world, if you will, the Bangladeshs of the world, where sea level rise will inundate land area and cause migration. I would argue that sea level rise due to climate change and glacial melting is probably going to be more significant to the developed world. And that's because we live in a just-in-time economy. We are dependent upon our transportation systems being able to transmit goods and services back at high rates of speed and almost instantly. Although, if you listen to our current president, he would just as soon isolate us, so maybe sea level rise is good for him, but we don't want to get into politics today if we can avoid it. So this is, how often have you taken off or landed at an airport and either seen the ocean as soon as you take off or seen it just before you land? Many airports, right? Most of the major metropolitan cities of the world, their airports are they're on the coast. And so the impacts to transportation is significant for sea level rise. So we have to understand, we have to begin to predict sea level rise due to glacial melting. And whether it's going to occur in 30 years, 300 years, or 3,000 years makes a big difference in our engineering world. For example, this is Hurricane Sandy. This is LaGuardia Airport in when it was 2012. So the airport, this is a little tough to land on unless you're a duck, I guess. LaGuardia, of course, is right at the ocean, right at the bay there, and was closed for about 7 days. And I think the cost was revenue loss of order of $500 million just for that one airport being closed. So understanding sea level rise, and this was obviously a big storm, but you raise sea level a meter, this happens not just once every 10 years, this happens once every 3 or 4 months. Okay, so with respect to what's going to cause sea level rise, two things are causing sea level rise. One is the simple warming of the ocean, so the thermal expansion of the ocean. As the air temperatures warm, the ocean also warms. The second is ice sheet melting. And the two major ice sheet areas of the world, Greenland and Antarctica. Particular interest is West Antarctica, and I'll give you a map of Antarctica in just a second, just to orient yourself where you are. But most of the West Antarctic ice sheet, this big glacier, huge, enormous ice sheet, is grounded below sea level and has the potential to go runaway melt, runaway collapse. I'll talk about kind of why that is in just a second. And this could occur not just at the slow process of slowly melting and rising sea level in 300 years, but it's possible it could rise sea level several meters in, give me a time frame, 10 years, 30 years, relatively quite quickly in our lifetime, and have significant impact on our engineering structures and our livelihoods. Yet we really don't understand very well the melting process. So here's just a map, or just a schematic, of what these ice sheets and ice shelves look like. This is similar to what you might see in Greenland as well, but this is specific to West Antarctica. So this is the ice sheet. This is the part of the ice that's above sea level. Well, all of it's above sea level, but this is the part that we think of as a big glacier. It's grounded on solid Earth. It's grounded, but that grounding line, or that topography, slopes backward toward, I'll get over here and use my pointer, towards the South Pole. Okay, so unlike most glaciers that are kind of running down mountains toward the sea, this is a case where these glaciers are actually running, if you will, uphill toward the ocean. Okay, and the reason for this is snow accumulation. This is the ice shelf. This is the part of the glacier that is actually floating, and it is where we produce icebergs and calving and things like this that pop off here all the time. Okay, so this is we have motion from here to here. And again, this has been going on for millennia, if not millions of years in the Antarctic. The ice is formed on the left and makes its way to the right. But why is it that this could collapse, unlike most glaciers that are grounded above sea level? This bed slope allows warm ocean water to come to the grounding line. That's the point where the glacier is actually on the ground. As we move that grounding line back, we have less friction holding the rest of the glacier in place, and it starts to move. Okay? And what's important is that the flux across, the ice flux across this line here, here's the grounding line, the velocity, or the flux, not the velocity, but the flux across there, is a function of the thickness of this ice. So if I move this grounding line back to here, the ice is actually thicker, and therefore its flux will increase. So it's a feedback process that essentially, as the grounding line moves backward and deepens, then this ice moves faster out to the ocean, and as a result can collapse, if you will. It's not really collapsing, but it's essentially melting. And of course, any of this ice that's below sea level doesn't affect sea level rise, but it's all the ice that's above sea level is what will cause the sea level rise. Okay, so just to give you a little bit of geometry of Antarctica, for those of you who are not familiar, it's often difficult to think of east and west when you're down at the bottom of the Earth, but we will. So South Pole is somewhere in here. This is East Antarctica. Most of this ice is actually grounded above sea level. Okay, so it's typical what we would think of a glacier is that the ice is on solid rock. Just for orientation, South America is over here, South Africa is over here, Australia and New Zealand are down here. And this is West Antarctica. And essentially, if we melted this ice, took this ice away, what we would see is more of an archipelago of islands in West Antarctica as opposed to solid Earth, which we would see, or above sea level landscape here. And West Antarctic, the ice sheet, which is here, is making its way north. They're all going northward because you're near the South Pole, moving northward to this ice shelf here, which is the Rhone and Filchner ice shelves, moving this direction down to the Ross ice shelf. So this is all floating ice down here. And then also moving outward onto ice shelves here along the west coast. Okay, and this is where it's actually moving the quickest right now. Okay, just to give you, and this is sea ice all the way around on the outside. Okay. So again, just to get a sense of these ice shelves, the floating part, so this is what you would see if you drive up to one of those big ice shelves. This is sea ice. and this is the ice, glacier ice here. And down underneath us, of course, is another about 10 times that amount of ice down below us. Okay, so this ice is making its way out and calving off just as icebergs would. So how is it we melt that water, that ice? What's the mechanisms for melting this and perhaps increasing the rate of melting, which will cause, again, this grounding line to migrate backward? There's a couple of different circulations that occur underneath these big ice shelves, and this is very much exaggerated vertically. Just to give you a sense of scale, this might be 200 meters or 150 meters here. This distance here from the ocean, the sea ice, to the grounding line might be 300 or 400 kilometers. Okay, so this is a big, thin ice shelf. Okay, I just drew it here so you can see it a little better, or Mike Craven did. So a couple of different ways we can melt this ice shelf. Most of the melting does occur from seawater. Not very much occurs from melting on the surface. Okay, the water is a much better source of heat. So we can move water, circumpolar deep water, which is relatively warm water, several hundred meters at depth. That can migrate from moving around Antarctica, moving in this way. It's quite warm. It's plus a few degrees C, and it can move in and melt. That's a really effective way to melt this and destabilize this ice shelf. This is what we think is really the prime driver. We can also have a circulation cell that forms due to sea ice formation, and because of this sloping bed, we actually generate a current that moves downward along the sloping bed because it's dense water, it's higher in salinity, and it moves down to the grounding line and actually melts at the grounding line because of the pressure dependence of the melting point of ice. And then finally, we can also push surface water from the ocean. Just from winds, we can move water in underneath the ice shelf from when there's ice-free conditions in the summertime. And that's pretty much what we're going to see. I'm going to show you data that shows this kind of circulation going on. So this is just an example of how these ice shelves fail. This is the Pine Island Glacier, and the U.S. was involved with research on this side, fortunately. But this crack was observed in 2012, and just to give you a sense of its scale, there's Boulder, there's Denver. So this is a big chunk of ice that broke off. This is not the big Larsen C shelf that just broke off a few years ago. That's much bigger, but this is collapsing off. And again, this part of the ice shelf here is also floating. So it's probably several hundred meters thick of ice here. And this is a very rapidly moving ice shelf and out to sea. Again, a normal process, but being accelerated potentially by melting up underneath the shelf. So how are we going to measure this? How are we going to monitor what's going on underneath these ice shelves? Again, think of the geometry, several hundred meters deep and several hundred kilometers inward. So these are huge cavities underneath the ice. It's very difficult to get there. Obviously, the logistics, it's hard to drill through them. It's expensive. Anything we drop down below the ice, through the ice into the ocean below, to look at mixing processes, they're going to freeze into the ice. We're never going to be able to retrieve them. So calibration or drift is a real issue. How we keep things powered over the Antarctic over the winter, it's always challenging. And the things that are interest to the oceanographers are temperature, currents, the depth at which these temperatures are, and then also the conductivity or the salinity. And today I'm just going to talk to you about how we can measure temperature at high resolution. So we put together a team from Ohio State University and New York University to go and drill through one of these ice shelves to prove that we could develop a simple technique to measure temperature in the ocean below and also the temperature in the ice, and perhaps look at how fast this ice shelf is melting. Here's just a schematic. Here's the ice sheet. You can see it's grounded below sea level, and this gives you a little bit more of the sense of the scale. This is several kilometers above sea level. And the ice shelf sits out here and then breaks off, and we're going to drill our way right through there. Okay? And it's about 180 meters of ice, and it's about 800 meters of ocean below this. And we're going to use fiber optic cables for fiber optic sensing for temperature measurement. Okay? How many have heard or know of just fiber optic temperature sensing? Okay, a little bit. We'll go really quickly through it. If you need more, I can blather on about it for hours if you like. So try not to bore you too much. But it's using measurement of temperature using only the optical properties of a fiber optic cable, the changes in optical properties due to temperature. Our optical fiber serves as the thermometer, and we use a laser to basically power that thermometer to provide the energy source for it. I can make measurements of temperature, resolve temperature every 10 to 25 centimeters these days. This is a little bit of an older slide. I can measure temperatures as far as 50 kilometers now on a single cable, and I can make those measurements even slightly faster than 1 hertz. So I can get 1 hertz data, 50 kilometers, every 10 centimeters of temperature on an optical fiber. Okay. If I slow down and for a resolution of about 0.5 degrees C. If I slow down or integrate longer with these devices, and I'm basically collecting photons that are backscattered to me, I can get temperatures now down to maybe as low resolution, as low as 0.01 degrees C. So quite high resolution temperatures as well. Okay, and there's some significant advances for atmospheric things that we can talk about afterwards that are allowing us to look a little bit higher frequency in the atmosphere. What are the advantages of it? Well, optical fiber is pretty cheap. I brought a few pieces of it with me. I will pass this around. So this is the cable we're actually going to talk about in the field. It's armored, and if you look very carefully, you will see the optical fibers sticking out. There's 2 there, and I've stripped off the plastic on one of them so you can see. Do not stick it in your eye. Okay, it would hurt. It's very small. Okay, nice thing about it, they can be quite small. We can actually just use almost bare fiber out in the field, so small thermal inertia. Think of a fine wire thermocouple. Once we put something out there, it doesn't move. Okay, it just sits in the environment so we don't disturb the environment. We can get high resolution measurements in time and in space. Okay? For those of us in the hydrology world, we're interested in high resolution space and time measurements. I can look at a weather station and I can get a continuous record in time of, let's say, precipitation, but I can't get that across the landscape. Or I can look at a satellite imagery and I can get perhaps precipitation across the landscape, but at one moment in time. Okay, with optical fibers, and if I lay fiber out across the landscape, I can now measure temperature at high spatial and temporal resolution. I continuously do it. So it's pretty powerful. And what's typical optical fiber look like? Again, what I sent around is two glasses, the core glass and the cladding glass. Okay, typical diameter for the core glass is somewhere around 50 microns. On the outside of that is a cladding glass with a different refractive index. Does everybody know how optical fibers work? I've seen lots of nodding heads, so I'll go through. I don't need to tell you too much about it. By the time we build it all up, we're at 125 microns, so a little bit bigger than a human hair. Then we put some plastic over it, and then we put more stuff on top of it for armoring it, depending upon the environment we might want to go in. If I want to just look at atmospheric profiling of temperatures, I can almost use just the bare fiber, as long as I can strain relief it somehow. If I'm interested in going deep in the ocean, well, now I have to protect that fiber from radial strain, from pressure, as well as from other stresses and strains. And so we get a bigger cable with other strength elements into it. So again, fiber optics work. Here's my core glass. A cross-section around of that is the cladding glass. And essentially, fiber optic transmission of information works by having complete internal refraction. So I send a photon in here. It interfaces with this contrast between refractive index material, and this is a very simplified view. There's a lot of variations on this, but that photon, if you will, is then refracted and stays inside the core glass and transmits information all the way down. So amazing stuff, sometimes called a light pipe. So how does it work for temperature? Well, I send a very short pulse of infrared laser light down an optical fiber. Most of those photons go all the way down to the end of the fiber. A few of them do interact and scatter with internal, basically they're the unlucky photons who are interacting with the molecules of the glass itself, and some of those then are scattered. Okay? So what you're looking at here, in fact, is Rayleigh scattering. The projector is putting blue light onto the screen, and you're seeing the blue light coming back. So a typical Rayleigh scattering, which is an elastic scattering. You get what you pay for. You get whatever you put in. Raman and Brion scattering are inelastic scatterings. They actually are absorbed by either the molecule or the electron systems, and then are re-emitted, but at different energy levels. So they're inelastic, either higher or lower levels. Okay? And again, the scattering is just the native silicon dioxide that's in the glass, or germanium oxide, or we can dope the fibers with other stuff that will cause more scattering. But most communication fibers, they don't want to dope it. They want all those photons to go to the end. Okay, so it's just nice, clean glass. So again, scattering, we send some photons in. Let's just go through this. Don't need to. There's the important one. Every once in a while, I'll have a scattering event, which instead of sending the photons out at too steep of an angle and are lost or down the glass, that photon then makes its way back upstream. Okay, it's scattered backwards and is internally refracted and comes back to a detector. So this is what I'm measuring, is I'm interested in these photons that are returning. This is exactly like LiDAR, except we're in the inelastic range, so it's Raman LiDAR, and we're using the scattering that's going on inside the glass. Okay? And the Raman scattering is a function of the energy status or energy state of that scattering site. That's how I get temperature out of it. Okay, how do I know where the light came from? Well, I send a very short pulse of light, let's say 10 nanoseconds. So I send a 10 nanosecond square wave. That goes about 2 meters in 10 nanoseconds. During that first 10 nanoseconds, I open my detectors back at the box. Light's going down. I start to see scattering in that first 10 nanoseconds of any light that has gone from 0 to 2 meters. So 1 meter out, 1 meter back. I've collected all those photons that have been scattered in that first 1 meter. It's kind of like a flashlight in a dusty room. You're seeing the scattered light. The color, if you will, and the amount of those photons coming back is a function of the temperature. Okay? And so I do that once. Then I open the detector again for another, let's say, 10 nanoseconds. Now I've interrogated the next meter of the fiber, anything that's gone down a meter, down 2 meters and come back. And I keep doing that until the light's all the way to the end of the fiber, and then I do that process again. Okay, so I'm basically accumulating photons all the way down. So it's no different than radar or atmospheric LiDAR, if you will, for particulate matter. Okay, and here 10 nanoseconds. These days, our lasers, our systems are operating at 1 to even half a nanosecond frequency. Okay, so here's what it looks like. I have a box, I fire a laser down, and I get backscattered light, and from that backscatter intensity, I can calculate a temperature. Okay, this is something that is widely used. It was developed for oil and gas. High-tension electric transmission cables, almost all of those will have optical fibers spun into the cables for temperature measurements. Since the utility people are interested, do we have any hot spots on these big cables? If we do, then we need to deal with that because that's where the powered cable will begin to fail. Okay? For us in the environmental community, we have been a new market for these companies. They're like, this is interesting. What can we use? What can we do with this? And a lot. So first off, then let's take a look. We're going to drop an optical fiber into the Ross Ice Shelf. So let's make our way there. Again for geography. New Zealand is off here, South America's there. The main US base in the Antarctic is McMurdo Station. You fly in, you actually land on, in this case, it's sea ice. It can also be glacier ice. And if you're lucky, you get on a plane and off you go to your field site. Okay, if you're unlucky, you go to McMurdo, which I think is kind of like Rock Springs, Wyoming. If you've ever been, those of you who have been to Rock Springs know, it's not the greatest place to be. Anyway, you try to get out as fast as possible. All your gear's has been all sent down, months ahead of time. In theory, it's the worst place for a procrastinating scientist in the world. You got to be organized. So everything goes down. You put it on low ground pressure vehicles, and then for us, we sledged our way out across one of these ice shelves. And so we are on about 200 meters of ice here, and about 1.5 kilometers of ocean below us. These are the Mount Erebus and Mount Terror of Ross Island, and we're going to go out and drill. So this is what our field camp looked like. We're out, again, on top of a floating ice shelf. We're going to drill through this and see if we can measure temperatures in the ice. Okay. well, how did we get there? Well, first off, we drilled our way through with just a traditional core drill to get our way down. But the problem with that is we're going down with an electric core drill, and we've got ocean water and electricity and seawater usually don't mix very well. So the idea was we had to stop within a few meters of the ice-ocean interface, pull out, and then we were actually going to melt our way through with a hot point melter, basically an iron, melt our way down to get down for the last little bit. The problem was because when we were all done, the borehole was going to be about 40 millimeters in diameter at the bottom. It was probably going to refreeze shut in about 20 minutes, so everything had to go down the hole pretty quickly and get in before the hole refroze. Turned out it was more like 2 hours, but still, it was an exciting time. This is the drill we used, very easy, portable drill. We would take 1 meter cores, and pretty quickly, in about 24 hours of drilling time, we could get down through the almost 200 meters of ice. This is what an ice core looks like. For those of you who haven't seen it, this is where the little dark spots here are actually gas bubbles, and this is where we would look at, if we were interested in this particular site, looking at CO2 and other trace gases that were in the atmosphere at the time that those bubbles were when the firn became solid and the bubbles became isolated. So one of the issues we had, I'll explain this graph in a minute, I'll show a couple times. The drama we had was we knew the ice shelf thickness to within about 10%. So 10% of 200 meters is 20 meters. So I didn't know where the ice-ocean interface was. And it was kind of important because we didn't want to drill through it. Again, electricity, seawater, kind of get the idea. So what are we going to do? Well, this red line, I said, well, let's drill down to about, 180 meters. We know we're not going to hit ocean there. Stop. And we lowered an optical fiber down into this open borehole, no water in it. And we lowered it down, and this is the temperature profile we got after about 2 or 3 hours, just letting it equilibrate. Okay? So each one of these crosses represents a temperature measurement integrated over a meter of the optical fiber. So a couple of important things on the red line. Let's not look at the blue line yet. First off, the temperature profile is curved down to the ocean. The ocean's going to be right about there. Okay, why is the temperature profile curved? That is a question to remember for your next PhD oral exam. You can ask your students this question. I will ask you, there'll be a quiz afterwards. We'll talk about why it's curved later. But what's really cool, and this shows what distributed temperature sensing is useful for, I actually know what the temperature of the ice-ocean interface has to be. It has to be at the pressure freezing point of seawater, which in this case, for 200 meters or so, is about minus 1.9 C. So I know the temperature of the interface, and now I have this incredibly high-resolution temperature profile that's showing me a beautiful representation of the gradient. Okay? Unlike if I'd had, 3 temperature measurements, some sensors, boom, 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 I'd have a pretty lousy picture of the gradient. But here, because I've got so many points, I've got a beautiful idea what the gradient looks like. So why don't I just extend this or fit an exponential to this and say, where's that exponential, because it's sort of exponential shape, where's it going to hit minus 1.9 C? And that's what we did. We said, okay, the ice-ocean interface is going to be at right about there. No, right there. Right there, sorry. And we said, okay, drill a few more meters, pull it out. Now let's melt through. And we tagged the interface within about a meter. So that was pretty cool. I was a hero. Later, I was not a hero for other problems that we had. But that was like, hey, that worked pretty well. But this is what I want to get the idea across is that this measurement, rather than having just individual points, the high resolution tells us something about thermal gradients. And we can learn a heck of a lot from thermal gradients, not just from individual points. Okay, the blue line is that as soon as we poked into the ocean, we lowered our optical fiber down as fast as we could because we thought we had 20 minutes, and we plugged it in and we started measuring temperatures. Okay, so this is over one day. It's about 18 hours. The blue line is repeating itself. And what's happening is down here again, the ocean is all at minus 1.9. It's nice uniform temperature. Don't worry about why it gets bigger here. There's some cool features that were going on as the borehole was freezing in with seawater. Okay, we were excluding salts. and we were probably having little bits of circulation cells that were going on in this slowly slush-filled borehole. And then this is as far up as the seawater rose to, okay? Because remember, the ice will float with about, 9 to 1, 9 feet of ice, 1 foot of freeboard, okay? So this is in the, that's where the ocean came up to in the borehole. And that's enough. Okay, so, all right. So this is when we were all done, this is what it looked like. Here's our 200 meters of ice shelf. We actually drilled 2 holes. I'm only going to show you data from one. The other hole was just to practice and make sure we could actually do this. And we have fiber optic cable that runs down through 200 meters and then goes down to almost 800 meters below the top of the ice shelf, so 600 meters of ocean. We also had independent pressure and temperature sensors at the bottom of or on these cables in a few places, because fiber optic temperature sensing only returns photons. It doesn't tell you temperature. So you need to have independent temperature measurements along the optical fiber in order to calibrate the system. Okay? And so these were high resolution temperature sensors, and also pressure, which would tell us how much the mooring would swing back and forth in the currents. And here's some results. So we ran the system for a full year. This is only sort of summer into the late fall, and I'm just showing you here. We were able to keep the system operating at very low power, doing a whole bunch of tricks. We collected of order 3.5 million individual temperature measurements. This is just the ocean profile. So here's the bottom of the ice, and this is then all ocean. You can see most of the ocean is a beautiful constant temperature bath at about -2 degrees C. But then on the bottom is time, and as we come into, remember we're in the southern hemisphere, so January, February, March is our summertime. As we come into summer and into fall, we start to see warm water underneath the ice shelf. Okay, and it turns out that's surface water from the Ross Sea making its way up underneath the ice. And when I say warm, it gets as much as, I think, about -1. Here's just some easier ways to see it. This is some time slices. Here's March, early part of March, and here's the ice-ocean interfaces right here. You can see we got water temperatures up about -1.1, plenty enough to melt the ice underneath. Okay, and then as we go down, this is early in the season. Important for those of us, you who are measurement people, you can see the wiggle, and essentially this should all be the same temperature. Down here, we're in kind of a constant temperature bath in the ocean, and the wiggle is the instrument noise. Okay, and so you can see our scale here goes from -2 degrees C to -1 degree C, and the instrument noise here was of order 0.03 degrees down at the bottom and about 0.02 degrees up in here. Okay, this is real. So that just gives you a sense of what kind of temperature resolution we can get. All right, so the most important thing for us, well, the oceanographers were interested in that warm water coming in, but I was interested in how fast is the bottom of the ice shelf melting. Okay, because that's really going to tell us the stability of this ice. Okay, well, the neat thing is we have a thermometer that is frozen into the ice and then in the ocean below, hanging down there. And again, I can measure the thermal gradient really, really well in that profile in the ice, and I know the temperature that the water has to be at the ice-ocean interface. It's at the pressure melting point of seawater at that salinity. If we assume the salinity is constant, and it's close enough to constant that it is. So one of my students said, you know, I have an idea. And he said, why don't we, let me step back. Here's a temperature profile in the ice now. So again, the ocean's right there. The temperature in the ice from over a full year, from January 2012 to January 2013, pretty much all the same temperature, right? Nice resolution there. But let's blow up the bottom few meters of this profile. And if I do, here's 2012, and again, extrapolate to that pressure freezing point of water, and I have a nice straight line. So there's my ice-ocean interface. I'm just making a guess here from this plot, -1.9, maybe right there. A year later is this black line. This is the temperature profile. Where's my -1.9 point? Well, it's about a meter up. Okay, so just by tracking the gradient every day, okay, and because I can resolve the gradient really well, I can estimate that interface position extremely well every day. And if I can do that, then I can tell you the melting rate. Okay, and that's what Scott Cobbs did, and a couple of us. And this is now in time. This is over a full year period on the bottom axis. This is the position of the ice-ocean interface, so down 192 meters. And the blue lines and red lines are a little bit different way of averaging the data, but let's just look at the black lines. And the melt rates then, this is the rate of change of that interface. It's about a millimeter per day melt rate up until sometime in the end of January. Melt rate increases to about 8 millimeters per day, then seems to flatten out back to 1 millimeter per day. Then it got dark, and we had some problems with our power system. So the system shut itself off through the winter. That was a problem. But magically, when the sun came back up, the solar panels came on, the system said, I got enough juice, I'm going to turn on. When it turned on, here's the position of the ice-ocean interface 5 months later. No fidgeting, no doing anything. You know, if I was to extrapolate that 1 millimeter melt line, I'd be pretty close to this point. Okay? Nothing happening again until just as we get into January again, and the melt rate starts to increase again. Okay, and why is that? Because, let's see, here's the graph. So up on top is the position of the ice-ocean interface. This is the ocean temperatures, and you'll start to see in February and March we started to get warm water, and these are times when the instrument was not working. We start to get warm water underneath the ice shelf, and that position of the ice shelf moves up. The draft decreases, okay? And then as we'll get out here a little ways more, you'll see it start to flatten out as this warm water is pushed back out to the ocean from internal circulation. Okay, so again, kind of flattens out. So what's neat about this is an instrument that we had in the field that measures temperature, integrates over a meter of optical fiber. And so it can resolve typically temperature fluctuations over 2 meters, Nyquist kind of stuff. We were able to resolve melt rates at a millimeter per day from those individual 1 meter measurements. So you can get a lot out of this kind of instrumentation if you think about it. And again, it all comes down to not the absolute temperature, but the gradient. And if we can resolve the gradient, we can learn a tremendous amount about what's going on. Here we're lucky again because we know what that bottom boundary temperature has to be. Has to be the pressure freezing point. Okay. All right. So with that, what else are we doing? Well, we've done quite a bit of other work in Antarctica. There's a lot of interest in these subglacial lakes, some of these big lakes that are underneath the ice shelves in Antarctica. So we've helped out with heat flux measurements, some recent work by Andy Fisher and his group. We're also supporting a project in another glacial lake that's about 20 meters thick that's just about to go. And then we're involved now with the Thwaites Glacier Monitoring Program, which is a big US-UK 5-year program to measure what we think are the most unstable of the ice shelves of West Antarctica, which are on that western part between McMurdo Station and the peninsula that goes up. So this is some work, collaboration with CU folks as well. So here we're going to put in at least 3, if not 5 or 6 moorings like we did at this other site in the Ross Sea to measure temperatures continuously over the 5-year, or at least a couple-year program. A lot more logistics, a lot more issues of electricity, but we'll get there. Okay, so this is where Thwaites is out in here. Okay, and so this is the ice that is really surging out to the ocean that is of significant concern. Some thought that as much as 10% of the current sea level rise is due to meltwater that is coming out from this portion of Antarctica. So it's everybody's interest. What else can we see with distributed temperature sensing? Got a few minutes. We'll throw a few other things out to you just to be thinking about other things we can observe. We can do quite a bit in rivers and lakes. We can drop cables down into lakes. We can also measure temperature along rivers so that we can look at groundwater coming in and look at fish habitat, things like that, understand the temporal and seasonal dynamics of stream temperatures, and we can do some snowmelt dynamics in forest terrain. So this is just the plot. This is Shasta Reservoir in California. It's the largest reservoir in California, and this is depth, And this is time along here. It's not quite a year's worth of time. And then this is temperature, in this case, every 15 centimeters in the lake. And this is a crazy lake because it has super hot water at the surface. Sorry about being in Fahrenheit. Data came from NOAA, so you never, NOAA might know. It's okay. No. Almost 80-degree water at the surface. All the bass fishermen are happy up here, and sort of 45-degree water down here. All the trout fishermen are happy down here. And the issue for Shasta Reservoir is it feeds the Sacramento River, and the Sacramento River has several different runs of endangered Chinook salmon. And so the Bureau of Reclamation that operates this reservoir has to maintain cold water in their reservoir in order to release cold water downstream so that they don't cook the fish as they're coming up the Sacramento River. And this is a big deal because not only do they have to protect the fish, they also have to provide water for downstream agriculture. This is the state water project, the main reservoir for the state project. Federal project. Federal. And also they have to provide electricity. So it's this huge balancing act, and they need to know high resolution how much cold water do they have at any one time. And in the past, all they would do is every 2 weeks, they'd send somebody out with a thermometer, a digital thermometer, obviously, and record temperature, do a CTD, a cast down into the lake in one place. So this is much easier, and they can get real-time temperature measurements. Let's talk quickly about fish. So anybody heard of the devil's hole pupfish? It's the coolest fish in the world, okay? It's about that big, okay? It's a little tiny fish. It lives in the smallest habitat of any vertebrate animal in the world. It's literally, I'll just show you a picture of it right here. This is where it lives, is in this fractured, open fracture. So this is not a cave, but it's limestone-rich terrain, but it's this open fracture down near Death Valley, and this is the size of their pond that they live in. Okay, so you can get a sense. These are divers in there. So it's like 2 meters by 7 meters this way. Now, it's really deep, okay? But it's super warm water, 35, 33 degrees C water, so it's tough for fish to live here. These fish have been isolated. There's no connection for these fish to get anywhere else. This is the only place they live. How they got there, that's a whole nother lecture of unknown proportion, how they got there, because they're way down. It's quite deep here. It's about probably 15 or 20 meters down to this water surface, below the land surface. But the question is, what are these poor fish going to do under a warming climate? And in this case, the interesting thing is that it's not that the atmosphere warms the water. It's that the water is sensible heat flux is out to the atmosphere at all times. So the average temperature of the water is warmer than the mean annual air temperature. So as you raise the annual air temperature, this water simply can't cool as much. And so the fish are going to be subject to warmer and warmer water. It's long flow geothermal systems. Here's what the place looks like. And in looking in this direction, so I was showing you across here, the divers were, right there. It's this long fracture that goes down at least 150 meters. If I turn that picture and now look at it this way, it's actually a pretty big room here. Okay, and the fish are living all in here. There's only, at one point they were down to 35 fish. It's a fish that has gone to the Supreme Court and won. Okay, so what we did was we said, well, what's the energy balance in this thing? What does the temperatures do during the season, and also where's the food for these fish as well? So we dropped fiber optic cables down into it and ran for about 2 years temperature measurements. And what's really neat is this is in the wintertime temperature profiles. And again, look at the scale here, 33.9. This whole range is less than a half a degree C. Okay, in January time frame, the water column actually overturns. Okay, because the water is warmer than the air, which is a little opposite of what we normally think, but it's warm water. So it overturns. And then in the summertime, it actually stabilizes, again, somewhat opposite, and then it's actually slightly cooler at the surface than at depth. Again, these are really small gradients, so you can maintain a thermal gradient like that and not have overturning. So just even understanding this is important for how food gets moved through this system. The only source of food for these fish is basically algae that live short periods of time near the surface, and then also wind-blown organic matter. The groundwater, this is all groundwater fed, there's essentially no food for them. Okay, under trees, well, it's easy to measure percent snow cover area when there's no trees, because I can see it with satellites, I can see it with the really neat aircraft you guys have. Really, I was impressed. Okay, but what happens if there are trees? Fly low? I don't think so. Okay, so are there some things we can do looking down? So this is a research station in California run by UC Berkeley, and these are trees. We're looking down, and you can see in this, and this is in the springtime, is that probably the percent snow-covered area is maybe, I don't know, 50, 60%. But it's pretty hard to see what's going on underneath these trees in this environment. This is a thermal image of the same environment as well. You can see the trees are much warmer in the snow. So what about under the trees? Okay. Well, why not lay a DTS cable, a fiber optic cable, out through the forest before it snows in the fall, and then as the snow begins to melt, what's going to happen? Any piece of that fiber that's underneath the snow during the day is going to stay at essentially 0 degrees C, or pretty close to it. But any fiber that's out here in bare ground is going to warm up during the day above 0 and probably cool off below 0 at night. Okay, so all we want to do then is every day is if we take, let's say we take a measurement of temperature along an optical fiber once an hour, and then calculate the variance or the standard deviation in time over that 24 hours. Well, if the standard deviation is low, I'm under snow. If the standard deviation is high, I'm bare ground. And then I can map that every day. So I can now get the evolution of the percent snow covered area daily with just having cable laid around. And rodents and things don't like to eat this cable. In fact, I brought this along. Here's the cable we use for this environment. Okay? And that's like $2 a meter, so it's not expensive, but it's got rodent-proof steel on it. And, okay, busy plot, sorry. Let's just look real quickly. This is distance along the optical fiber, so this is through the forest from here out to about 1,500 meters in this case, weaved all through a forest. This is time through March, okay? So March 10th through probably mid-April. And this is just a color-coded map of the standard deviation of temperature, so sigma t. Every place here before about March 30, almost every place is pretty small variance, or sigma, standard deviation. This is all snow-covered. Then as we progress in time, there's some places that do stay snow-covered, like this, but then there's other places that melt out, and those get bigger and bigger and bigger. And what you can see is in a few places, these are snow patches that are essentially just getting smaller and smaller from both ends. Okay, so this patch of snow all of a sudden became a patch, and then it's getting smaller, 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 and finally is gone at about end of April in this case. Okay? You can see here, it snowed one day. So you can see this blue line. We had snow that covered most of the site, but it probably melted in that same day. So we ended up with a little bit of snow cover for a day or so in that site. Okay, so very easy, low-cost ways then to compare, to measure snow-covered area. And so we've got some work that's it's in review that compares NASA's Airborne Snow Laboratory fractional snow-covered area to some of these data in the field. Okay, a couple more minutes, and I'll just end up. So you're all now convinced that fiber optic sensing is the greatest thing since sliced bread. There's some other cool acoustic fiber optic sensing we can talk about afterwards, but it's pretty neat. But after doing this for a few years through our instrument center, we said, well, what's the next neat tool coming along? And the next neat tool for hydrologists anyway, there was a lot of talk of, well, do something with drones. So we convinced NSF that yes, we will do something with drones. And we focused for us, for hydrology, the hydrology community, on landscapes of sort of 1 to 10 square kilometers. That's our area of interest. If we go bigger, these aircraft don't work for large-scale operations. If we go smaller, then it's a bit too small for almost any hydrology. But let's look at that scale. Okay, it's a scale that's often ignored in many environmental sensing. So the first thing we did was, how many people have heard of structure from motion? Here, a couple of you. Many of you may not have. So let's take a look. The easiest thing we can do with drones, okay, is topography. And topography is really pretty useful for a lot of people. Okay, just understanding the topography of the land surface. So this is just an example I have. I was in a laboratory in Chile, a hydraulics lab, and they had this really cool concrete model of a dam structure that was kind of about the size of that room over there, okay, for the camera. And I just walked around with my cell phone and went tick, 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 took about 30 pictures of this thing, just at various angles, just walking around. And what you see here is each one of these little blue frames is the estimated position of where my camera was. Now, I was inside, so I didn't have any GPS on the phone. It wasn't working. But the camera positions have been calculated by common points where two or more of the photos saw the same place on the ground, some piece of the floor or my foot or something that was recognizable. Okay? From that, gets the camera positions. Okay? From that, then, we can fill in the rest of the points. Okay, boom. And then we can lay the photos over like that. And let me just clear the cameras off of here so it's a little easier to see. And hold on. And there's our structure, our dam structure, that was generated from about 30 cell phone pictures. That's a DEM of that concrete structure. Took about 5 minutes to take the pictures and probably about 20 minutes to reconstruct the topography. So what can I do with that? Well, I can then, there's the surface. I can now start running fluid mechanics, fluid dynamics codes over this to estimate flow, et cetera, et cetera. Okay? It's poor person's LiDAR. Okay? All it requires, and it's based upon principles of photogrammetry. In the old days, we made topographic maps. This is just computer-aided topographic measurements. And instead of using two cameras flying stereo together, we just use one camera and we move it around the landscape. Okay? So all of a sudden now, I can get LiDAR resolution topography from simply photography. Okay? So I'll just show you a couple of examples of that. Because LiDAR on a drone is still difficult. It's pretty easy to shoot the LiDAR, but it's pretty hard to know the exact position of the aircraft, which is what you need to know. That's a challenging part. All right, so this is close to your guys' home. This is the East River in Crested Butte, Colorado. And this is the topography of a piece of the East River. And you can see this river running through here. You can see bushes, okay? So this technique works nicely when there's no vegetation. If there is vegetation, we can filter out some of it. If it's very dense vegetation, you have to use LiDAR. There's no way this will work. But if it's sparsely vegetated, it's pretty good. And again, this was flown in about, I'm going to say, 2 flights of 15 minutes each with a standard camera. This is near infrared. This is NDVI over the same area, flown with a multispectral camera. And what we're interested in here, we're interested in a lot of things. One of the things we're interested in is how the groundwater interacts with the surface water and how the surface water may at times interact with the groundwater. And what in hydrology we call this hyporheic exchange, where we exchange surface water into the near subsurface and then it reappears. Okay, there's a lot of important chemistry and biology that goes on during those interactions. It's critical for fish and for invertebrates. So one of the things we said, I've got all these river meanders, and if I'm river water moving this way, why would I bother to go all the way around this meander when I can short circuit through this meander bend in the soil and come out over here? I would much rather do that. It's shorter. Distance is shorter. In the past, that's pretty hard to estimate how much of this shortcutting might actually occur because it's hard to measure the hydraulic gradient, the difference in hydraulic head between these two places. You have to have somebody stand out there with a stick and a staff rod. You need to know the hydraulic properties of the material. That's also difficult. But for us, when we flew this, we said, well, now, because we did a digital elevation model, we now have a map of the stream elevation or the water surface elevation all the way up this drainage. I'm going to show it here. This is now the reconstructed topography of the stream, the surface of the water, at centimeter resolution. And to get this in the field, you'd have to literally have somebody out there with a total station measuring, walking down the stream, measuring the surface water. And of course, as soon as you put a stick in the water, it rises up because of the velocity, hitting the stick. So this is a remote sensing way to get river topography. And what we can then do is we can estimate the hydraulic gradient across each one of these meander bends. We know something about the hydraulic conductivity. We can calculate the flux through these. And it turns out, not surprisingly, the fluid flux through any given one meander is probably about 0.01% of the total stream flow. Hardly anything. But it is important biologically, and if you add that up for a meandering stream that might have several hundred meanders in it, it begins to be an important exchange phenomenon. And we can now quantify it because we have the hydraulic gradient quite easily calculated. Okay? Last example, this is from a cornfield in Iowa. This is the Critical Zone Observatory in Iowa, one of the two CZOs associated with intensely managed agriculture, Critical Zone Observatory. And this is flown across the landscape of a flat cornfield before the corn was growing. Boring. Okay, it's flat, but I'm going to blow that picture up, and this is just using structure for motion. You can see the individual what do you call those? When they tillage, the plow furrows. Thank you, furrows. Here's tire tracks, so it gives you a sense of scale. Okay, and what's of interest to the group here is sediment transport and erosion. Well, okay, this is blown up from here, and I guess if you squint, maybe you can see something there. And if you squint not too hard, you can see this drainage that runs through here. And this drainage was essentially unobservable to anybody on the field. We're talking probably a centimeter of topographic difference. It's not even as deep as the wheel tracks here from the truck running over it. So from a series of 2 flights with a standard low-cost drone, we can now calculate the topography and produce these really high-resolution topographic maps. I think that's pretty cool. That's pretty neat. And again, with this technique, we do need to have some ground control points. We need to know the elevation of certain places. So you do have to do some GPS surveying or total station surveying. But it's really quite easy and inexpensive for bare ground, or relatively bare ground. Okay, I'll leave it at that. This is our instrument center. It's operated by NSF Instrumentation and Facilities in EAR. Again, CTEMS. So we provide DTS systems for NSF or anyone else, primarily NSF researchers, and now we also provide drone systems. Typically, these systems, we were talking about this earlier, these we kind of train people, the DTSs, how to use it. All the data comes back to our lab by cell modem. We have power systems. It's pretty turnkey, but we turn people loose with it. Say, go. You can't hurt yourself. Well, you could if you stuck the fiber in your eye. But beyond that, you can't hurt yourself. Go collect data, see what you can do. For the aircraft, for the drone stuff, drone surveys, we typically do provide a pilot because of FAA requirements. So we do get a little more involved, kind of like what your group here does. But I think that's enough. It's 4:30. I'll be quiet and take any questions you might have. Thank you. And I don't know how we do questions, whether there's from a distance or...
Yeah.
So you talked about the cost of the fibers. What about the
box?
The box, the LiDAR system, I guess.
Yeah.
It is.
So the question is, what's the cost of the LiDAR system? So that they've been coming down, sort of down in price, and typically the boxes themselves are about $20,000, $15,000 to $20,000. The high spatial and temporal resolution boxes are close to $50,000 still. And then on top of that, if you wanted to have something that would go out in the field, you need peripherals, a little bit of a cell modem, and a little bit of low-cost, low-power industrial PCs and things like that. But so it's not terribly expensive, but it's still not cheap. And the price doesn't seem to be coming down yet. It's come down a few times slightly, but the resolution has really increased. In the 10 years we've been doing this, we were happy if we could get 2-meter sampling at either 15 or 30-second integration times. And now we can do 10, 12 centimeters at, I think, 2 to 4 hertz. So the things have improved, but the price, you still get what you pay for, I guess.
So, bigger picture question. A lot of what you showed was for field campaigns of really short duration. Some of the CZOs have got longer duration. If you're stepping back and looking at the investment in hydrological research or environmental research generally, do you think that we've got it right?
So the question about whether the critical zone observatories, which are monitoring, trying to monitor for long periods of time, versus a lot of this stuff, which is campaign style, typically experiments. My view, what we've tried to do with this instrument center is to get this technology out to people, and we've had this happen quite a few times, is now people say, oh, I could buy one of these with my startup, and then they're off on their own. And then they don't have to call us. We don't send them any bills. They're off on their own, and they're monitoring for long periods of time. So that was our goal, this is sort of the fly on the surface of the water, kind of see if you can get them hooked into it, and then do it yourself, because it certainly is doable. And I think the unmanned aircraft is almost the same these days. Get people hooked into it a little bit. It's not that difficult to operate to a certain point. The bigger question, should hydrology be doing field campaigns or long-term experiments? I think we have to have long-term experiments. We really need to have those as hydrologists to get through the variation in runoff from year to year. But I'd love to see our hydrology community do a lot more field campaign work. Kind of jump, and we were talking about this earlier, is like this community, the atmospheric sciences community, really has that figured out. I think it builds camaraderie, it builds training, it builds a lot of things that we have in hydrology we have missed. And again, talking to the folks who've been involved with some of the big field campaigns, their lives are incredibly richer because of it, that are in our community. So, I'd love to see every big field campaign that's land surface, atmospheric transport have a hydrology component.
So as you've passed around the fiber samples, I can't help but being struck by how much thermal conductivity there is to the outer sheath, and wondering if that's spatially filtering the temperature signal that you're trying to measure. But yet your snow data seem to show fairly abrupt edges.
Yeah, so sort of two questions. One is, let's think of the thermal mass and the ability to change temperature. So the nice thing is that the heat fluxes are all radial in the cable, so they are relatively short distances. But some of the big cables that I've sent around to you will certainly have a time constant of somewhere 30 seconds, 2 minutes, something like that. So there's no question that if you wanted high frequency, temporal frequency measurements, you're going to filter out sort of probably up to 30 second, 60 second stuff. But if I just have bare fiber or fiber that has basically the inside of what that is, there the thermal mass is tiny, and so they will respond. Again, maybe not as fast as a fine wire thermocouple, but pretty close to that. But again, it is so there is this radial heat transfer that is quick. Now the other advantage is, I think you were referring to in the snow, we were measuring like once an hour for maybe a few minutes over the cable. So in an hour's time, that cable has plenty of time to warm up and cool down. In fact, I could take even one of these cables and hold it in my hands, and we would see in a few minutes it would warm up. There is also, though, the longitudinal heat transfer, this direction. Here again, if you think of the cross-section of that sheathing and everything else on it, it's pretty small cross-section. So the heat transfer is relatively small because the cross-section is relatively small. So you don't get a lot of bleed over thermally. But you do get bleed over is optically. So I send out a square wave of light, but by the time it goes down a kilometer, it's not a square wave anymore. It's a smooth wave because there are multiple paths the photons can take. So we do have some dispersion. And that's where we lose spatial resolution. So yeah, there's always going to be some, if I tell you I have an instrument that samples every meter, okay, I'm sampling that meter plus 10 or 20 centimeters on both sides. So I'm getting input from temperatures outside of that. So we do have a measure of that, and it's called we call it the spatial resolution, and it's over what length of a cable does the instrument need to see 80% of a step change. So I take a piece of fiber and I put it into a ice bath at a fixed position. How far does it take to get to 80% of 0 degrees C? And that's typically about twice the sample resolution, which is a meter. So it's a long-winded answer, but so there is bleed over, yes. And it gets worse the further you go because there's more dispersion of that nice square wave.
I have one question. What kind of power would have been required to operate through the darkness on the ice shelf?
Yeah, good question. So right now, it all depends on how rapidly you want to sample. And then in the case in the ice shelf, it was also, we were sending information back by satellite modem, which was the fairly large power consumer. We had a problem with a short circuit in a wind generator. We had enough power, but we had a short circuit at some point, and there was a current drain that killed our batteries. But we're going to be operating the Thwaites Glacier systems without, excluding data transmission, they'll be operating at less than a watt continuous. And that will be measuring probably about 6 or 8 times a day because it won't be continuous over time. It'll be a set of measurements, say for 5 minutes, go quiescent for 4 hours, turn back on. But we can get it down to a watt, roughly a watt, which is not bad. Yeah, that's the goal. That's tomorrow's meeting, is to make sure we can do that, test it.
Any other questions? Let's thank Scott again.
Thank you. Thank you.